So now in this lecture we solve the examples of total differential equation. Let us take example. Solve 3x square dx plus 3y square dy minus x cube plus y cube plus e raised to 2z dz is equal to 0. So solve this differential equation. So compare this differential equation with standard equation, that is p dx plus q dy plus r dz is equal to 0. Where what is p? P is 3x square. Therefore p is equal to 3x square. What is q? Q is equal to 3y square. What is r? R is equal to minus x cube plus y cube plus e raised to 2z. Okay? So this is PQR. So test the condition of integrability. So is it integrable or not? So what is the integrability condition? Therefore, what is p into bracket dou q by dou z minus dou r by dou y plus q into bracket dou r by dou x minus dou p by dou z plus r into bracket dou p by dou y minus dou q by dou x is equal to. So this is a condition of integrability. If this is equal to 0, putting this, then the equation is integrable, and we solve the example. Okay, further. So that is p is what here? 3x square. What is the dou q by dou z? Partial derivative of q with respect to z, keeping y constant. So that is 0. Then what is the dou r by dou y? Dou r by dou y, partial derivative of r with respect to y, keeping x and z constant. So that is minus plus. So what is the partial derivative of r with respect to with respect to y? So that is 3y square. Then what is q? Q is what? 3y square. What is the dou r by dou x? Partial derivative of r with respect to x, keeping y z constant. So minus 3x square minus dou p by dou z, dou p by dou z, partial derivative of p with respect to z, keeping x constant. So minus 0 plus. So that is r. R is this minus x cube plus y cube plus e raised to 2z. Okay, then what is the dou p by dou y? Partial derivative of p with respect to y, keeping x constant. So this is 0. Dou q by dou x, partial derivative of q with respect to x, keeping y constant. So this is 0. So that is 0 minus 0. So what happened here? So this is 9x square y square minus 9x square y square. So this is 0. Okay. So this condition is 0 here. Okay. Value of this condition is 0. Hence the given differential equation is integrable. Hence given equation is integrable. So what is the next part? So the given equation is integrable, nothing but the equation is solvable. Okay. Then what is the solution of the differential equation? So to find the integral put z is equal to constant. Put z is equal to constant. That is the dz is equal to 0. That is the dz is equal to 0. So you can put x constant or y constant or z constant. Let us take here z is a constant, so it is a derivative, so that is dz is equal to 0. So therefore, so if dz is equal to 0, therefore this equation becomes 3x square dx plus 3y square dy is equal to 0, since dz is equal to 0 here. So the equation becomes like that. Okay, so on integration, what is the integration of this? Taking integration, so what is this? Integration of x square dx, so that is x cube upon 3. X cube upon 3, 3 get cancelled, so that is x cube. What is the integration of this? So y cube upon 3, y square integration, y cube upon 3, 3 get cancelled, so y cube is equal to pi of z. This is integrating constant, because we put z is a constant. So this is a temporary constant. So z is not a constant. Just we take z is a constant. So this is a temporary constant here. Okay, pi of z. Then, so differentiate this. Differentiate this with respect to x, y, z. We get. So pi of z is a constant, but after then z is not constant. For this step only z is a constant. But x, y, z are the variable, throughout variable. So from this step, z is not a constant. So we differentiate this with respect to x, y, z. So what happens? So this is 3x square. 3x square dx. Plus this is, what is the derivative of this? 3y square dy is equal to, what is the derivative of this? So d phi by dz into derivative of z is dz. So derivative of this is d phi by dz into dz. So this equation becomes here. So that is 3x square dx plus 3y square dy minus d phi by dz into dz is equal to 0. Okay? So comparing this equation with given equation, comparing it with given equation, we get. Comparing it with given equation we get. So compare this equation with this equation. Then what happened? So what happened? 3x square dx is there here also. Then 3y square dy. Then what is the d phi by dz? So d phi by dz is equal to what? So d phi by dz is equal to minus d phi by dz is equal to this. So coefficient of dz. So d phi by dz is equal to, so this is x cube plus y cube plus e raised to 2z. Okay, e raised to 2z. But what is x cube plus y cube? X cube plus y cube is equal to pi z, or simply pi plus what? E raised to 2z. So we write here, so that is a d phi by dz is equal to minus pi is equal to e raised to 2z. So what is this? So this is the first order linear differential equation. Okay. So this is first order linear differential equation of the form dy by dx plus py is equal to q. So this equation is of the form dy by dx plus py is equal to q. So its solution is what? So we know what is the solution of this differential equation. Y into integrating factor is equal to integration of integrating factor into q dx plus c something. But here is phi is a dependent variable. Here y is a dependent variable. Here phi is a dependent variable. So phi into e raised to integration of p dz, z is an independent variable, is equal to integration of e raised to integration of p dz q dz plus c, that is integrating constant here. So therefore what happened? So phi is equal to e raised to what is p? What is p? Compare this. P is minus 1. So p is minus 1, so minus dz into is equal to e raised to minus dz. What is q? Q is minus 1. Q is e raised to 2z. This is p. And what is q? Q is e raised to 2z. E raised to 2z. dz plus c. So what is the integration of this? So that is phi into e raised to minus z is equal to, what is the integration of this? E raised to minus z into e raised to 2z dz plus c. Okay? Therefore, what happened here? So that is e raised to minus z plus 2z, e raised to z dz plus c. Okay? So dividing throughout e raised to minus z to this equation. So that is phi is equal to e raised to minus, so e raised to z into what? Just, okay, we obtain this integration also. So e raised to minus z. So then what is the integration of e raised to z? That is e raised to z plus c. E raised to z plus c. So dividing this throughout. So phi is equal to dividing this throughout. So that is divided by e raised to minus z. So to the numerator e raised to z into e raised to z, that is e raised to 2z plus c into e raised to z. So this is pi. Okay. So putting this value, what is pi here? We obtain pi. So this is equation 1. This is equation 2. So from 1 and 2. From 1 and 2, what happened here? So that is x cube plus y cube. X cube plus y cube. What is pi? Pi is this, e raised to 2z plus c e raised to z. So this is the required solution of the given differential equation. Okay. So here what is the method? Put z is equal to constant, or you put x constant or y constant, then solve the differential equation. This is one of the method here. Okay. This is the method. So we solve the another differential equation. Okay. Solve differential equation. So solve y plus z dx plus z plus x dy plus x plus y dz is equal to 0. Solve this differential equation. Okay? So comparing this equation with the standard equation, p dx plus q dy plus r dz is equal to 0. Then what is p? P is y plus z. What is q? Is z plus x. What is r? R is x plus y. Okay, now we test the integrability condition. So integrability condition is given here. So if integrability condition is satisfied, then the given differential equation is integrable, nothing but a solvable. The equation is solvable. Okay, so this equal to, so what is p? P is y plus z. Then, so what is dou q by dou z? Partial derivative of q with respect to z, keeping x constant, derivative of z with respect to z is 1. X constant 0. What is dou r by dou y? Partial derivative of r with respect to y, keeping x constant. So, derivative of r with respect to y is 1. Okay. Then q is what here? Q is z plus x. What is the dou r by dou x? So, what is the derivative of r with respect to x? Partial, keeping y constant, that is 1 minus 1 plus similarly r x plus y. So that is 1 minus 1. So this is again a 0. So this is 0. Hence the condition is satisfied. Therefore the given differential equation is integrable. Therefore the given equation is integrable. Okay, so we solve this differential equation. So there are so many methods, alternative methods. So previous example we put z is equal to constant, then dz is equal to 0, then comparing that equation with this equation, then integrable, again differentiate, and then find the solution here. So there are so many methods are there. So methods depends on the example. So how to solve this differential equation here? The given equation can be written as, so what happened? y dx plus x dy. Okay, then what? Just made y dx plus x dy, then z dy plus y dz plus z dx plus x dz is equal to 0. So we make exact part of this differential equation. So this is exact. So this is exact. So this is exact. So what happened here? So that is d of xy. So this is exact part. Derivative of this primitive xy. So that is y dx plus x dy. So derivative of this x as it is, then derivative of y dy, y as it is, then derivative of x dx. So this is the exact. What is the definition of exact differential equation? So you know about that. Okay. Plus d of yz. So this can be written as d of yz plus d of xz is equal to 0. So this is an alternative, very simple method. So method depends on the examples. On integration, what happened? So that is integration of this. So derivative and integration get cancelled. So that is xy plus yz plus xz is the integral constant c. So this is the required solution of this differential equation. So very simple. So now we take what is the geometrical representation of the total differential equation and ordinary differential equation. Okay, geometrical representation of a total differential equation P dx plus Q dy plus R dz is equal to 0. So what is this equation? How to represent this equation geometrically? So take a diagram. So this is the curve, space curve. So this is the point xyz. This is the curve in space. So this obtained by the primitive, so that is u is the function of x, y, z equal to c. So this equation nothing but a curve in a space. So this is the tangent at point P, and this is the normal at point P. So this is the 90 degree. Okay. Then what happened? Then dx, dy, dz and PQR. So we know that there are two lines. So LMN, L1, M1, N1 are the direction ratios of the line, this line, and L2, M2, N2 are the direction ratios of this line, and if those lines are perpendicular to each other, then what is the perpendicularity condition? So that is L1, L2 plus M1, M2 plus N1, N2 is equal to 0. So this is the perpendicularity condition. Okay. So L1, M1, N1 are the direction cosines of this line. L2, M2, N2 are the direction cosines of this line. Two are direction ratios. Then if two lines are perpendicular to each other, then this is the perpendicularity condition. So we use this condition here. So what is this? So this is L1, L2, M1, M2, N1, N2 and so on. So this is nothing but a perpendicularity condition. Okay. So we know that dx, dy, dz. What are the dx, dy, dz? So this is the what is the solution of this differential equation? Something u of x, y, z is equal to something c. This is the solution, and the solution nothing but a curve in a space. This is a curve. So we take P, X, Y, Z, be any point on that curve, and we draw the tangent at that point, and this is a normal. Then we know that dx, dy, dz are the direction ratios. Of the tangent at P. Okay, to the curve here. Okay, P to the curve. Further, if PQR are the direction ratios of the normal to the curve. Here dx, dy, dz are the direction ratios of the tangent, and PQR are the direction ratios of the normal. Then by perpendicularity condition, perpendicularity condition, perpendicular condition to the tangent is, condition is what? What? So this equation P dx plus Q dy plus R dz is equal to, okay. So what are this? So this equation represents here, so dx, dy, dz are the direction ratios of the tangent and PQ are the direction ratios of the normal, because this equation is also a perpendicularity condition. And we say that perpendicular condition, so dx, dy, dz are the direction ratios of the tangent and PQ are the direction ratios of the normal. So similarly, so what is the geometrical representation? Geometrical representation of what? So dx upon p, dy upon q is equal to dz upon r. Dx upon p, dy upon q, dz upon r. So this is the ordinary simultaneous differential equation. So how this equation represents geometrically? So that is important. So we draw again a curve. What is the solution of this differential is also a function of x, y, z, and that function is nothing but a curve in a space. So that is, this is the curve. So the curve here, and this is the point P, x, y, z on the curve. Okay. So this is the tangent. So this is the tangent at the point P. So let us consider, so dx, dy, dz are the direction ratios of the tangent at the point P, x, y, z, dx, dy, dz. Okay. So if two lines are parallel, if these are the lines, so something A1, B1, C1, A2, B2, C2. So these are the two lines. A1, B1, C1 are the direction ratios of this line. A2, B2, C2 are the direction ratios of the line. And if two lines are parallel, then what is the condition of parallelism? So that is A1 upon A2. So B1 upon B2. C1 upon C2. So we study this in the 12th standard. So this is very simple. So if dx, dy, dz are the direction ratios, and PQR also direction ratios, and those dx, dy, dz and PQR are in proportion, then PQR also direction ratios of this line are parallel to this line. So PQR also direction ratios of the tangent, and dx, dy, dz are also direction ratios of the tangent here by using these equations. Okay, we know that. So dx, dy, dz, dx, dy, dz represents the direction ratios of the tangent at P. Direction ratios of the tangent at P. Okay, to this curve. But what happened? But this equation are they simultaneous differential equation? But dx upon P, dy upon Q, dz upon R states that states that dx dy dz are proportional to what? PQR. Then this is a parallelism condition. Parallelism condition. Then PQR are the direction ratios. Ratios of the tangent at P. So these are the geometrical interpretation or representation of the total differential equation and ordinary simultaneous differential equation. And also, what is the relation between geometrically represent here the relation between the total differential equation and ordinary differential equations. Okay, how do they relate those two differential equations? So this is also important. So we take examples and what is the relation between these two equations to the next lecture. Okay, we stop here. Okay, thank you.